I want to take a real quick look with you guys at this question, which is actually question 8 at the end of section 1 here of part 1. It's called the SOS game, and they say it's from the 28th annual USA Mathematical Olympiad from 1999. Now, the USA Mathematical Olympiad is kind of the culmination of the contest sponsored by the MAA for high school students. They have 3 levels now. They have the American high school. I forget exactly what they call it. They've changed the names over the years. The American high school exam is what it might be called. And then they have a second level, and then they have this USA Mathematical Olympiad. Typically, it's only about the top 100 or so in the country of best high school students who even compete in the Mathematical Olympiad, and the top 15 or 20 get invited to some summer camp where they select the USA National Olympiad team for the International Olympiad that takes place over the summer, where the top students from the USA compete against the top students from all the other countries. Way back in 1982, I was a high school student, and I competed in the USA Mathematical Olympiad. I didn't make it to this the level where they invited me for the summer training and participation in the International Mathematical Olympiad, but it was still just great to even participate in the USA Mathematical Olympiad. It consists of 6 really hard problems. They're not advanced problems, as you'll see. They can be easily described, and typically they're accessible to all mathematically inclined high school students. They don't require advanced college mathematics, but they do require some sort of tricky analysis. And so this year they had a question that consisted of the analysis of a combinatorial game. Now, this combinatorial game isn't a win-lose game, as you'll see. It's a win-lose-draw game. So it's a game that can end in a win for one player, a loss for one player, a win for the other, or a draw. It is an impartial combinatorial game, though, because the rules are identical for both players, and the players alternate turns, as you'll see. So we start with a board that consists of n squares. I'll draw it for n equals 4 here. Instead of squares, I'll just put dashes there. Initially empty. Players take turns selecting an empty square and writing either an S or an O in it. The player who first succeeds in competing SOS in consecutive squares wins the game. If the whole board gets filled up without an SOS appearing consecutively anywhere, the game is a draw. So the first question is, suppose n equals 4, that's why I put 4 dashes here, and the first player puts an S in the first square. Show the second player can win. This is actually a winning position for player 2, or from the position it's in right now. This would be an N position. The next player to move can win the game. And so just by simple trial and error, one can figure out what to do. If the second player puts an S in the second square, then the second player certainly cannot force a win, because the first player can just put in another S, and it's impossible for anybody to win. If the second player puts an O here, the first player will get a win immediately by putting an S in the third position. If the second player puts an S in this third position, obviously the first player will go back and win with an O in the second position. If the second player puts an O in this third position, the first player can easily avoid a loss, at least, just by putting, say, another O there, and then no SOS can be made. But if the second player puts an S in position 4, then it's easy to see no matter what the first player does, the second player will win. If the first player puts an S here, the second player puts an O there and wins. If the first player puts an O here, the second player then just puts an S here and wins. And you can see very easily that we get the same sort of results if the first player puts an S here. The second player would put an O there, and I won't draw this out, but if the first player put an O there, then the second player would put an S there and win. So if the first player chooses to put an S in that first square, that's a win for player 2. So what does that tell us about the game with n equals 4? Well, it doesn't quite tell us everything. It just tells us the first player really shouldn't put an S in the first position. Is this game one which will lead to a win for the first player if the first player plays optimally? Or will it lead to a win for the second player if the second player plays optimally? Or will it end in a draw if both players play the best that they can? Here it's pretty easy. You should be able to convince yourself that with four squares it will lead to a draw. Why? Because if we just avoid putting an S in the first square, and by the way, the first player should also avoid putting an S in the last square for the same reason. The second player could respond with an S in the first square and win the game. If the first player avoids doing that and, say, puts an O in the first square, then it's very easy to see the second player can't force a win, because whatever the second player does, you can try each of the different possibilities very quickly. If the second player puts an S here, for example, the first player can block things. In fact, it's already blocked. There's no way for anybody to win at this point. If the second player instead put an O here, it's easy to see that SOS is impossible then. You can try all the different possibilities. If the second player puts an O there, things are impossible. If the second player puts an S all the way on the right, it's certainly possible for the second player to win if the first player puts an S there or an O there, but the first player can prevent that very easily by putting an O there or by putting an S there. So you'll see if the first player puts an O over on one side instead of an S, that will lead to a draw if players are playing well. What if the first player puts an S in the second position? I'll leave you to check the possibilities, but it's easy to see the second player can block the first player from winning very easily, and the first player can block the second player from winning. And the same is true if an O goes there, and similarly for that square. So this game will lead to a draw in the 4 square situation if both players play optimally. Part B of the question says, what if instead of having 4 squares, we have 7 squares? So I'll make it up to 7 squares. Then the first player can actually force a win. This initial position is an end position. The next player to go, which is the first player, can force a win. And it's easy to experiment a bit and see how this can happen. I'll show you the basic idea. If the first player plays an S in that first position, then we have several different possibilities. The second player might play an S here. Now this is a very interesting situation, these 4 squares. We're back to the first player now. If the first player plays an S or an O here or here, whatever the first player does in either of these squares, we kind of analyzed that in part A, then the second player can get a win. So the first player would not want to play either of those squares. So what can the first player do? Well, the first player can play an S here, and then that means in this group of 4, the second player, if the second player plays either of those, the first player wins, and if the second player plays either of those, the first player wins by filling in an SOS on whichever side is played. So what does that tell us? That tells us, assuming the first player played that S in the middle, the second player would not want to play an S over at the side, say on the left side or the right side, because that could be countered with the first player playing the opposite side and forcing a win. So let's say that the first player does literally anything else on the left side, anything other than an S on the left. If the first player plays, say, an O here, I'm sorry, that's the second player playing an O there, then the first player can respond in a manner similar to what we've seen before and play an S here. And then what happens? The second player can't play one of these 2 squares, because that would lead to a first player win on the right side. So the second player can play one of these, but then that can be blocked by the first player. Whatever the second player does just gets blocked by the first player, and that forces the second player to play one of these, and the first player ends up winning. So if the second player responded to that opening S in the middle with anything other than an S on the side, the first player would respond with an S on the opposite side, play out there if necessary, and force a win on the right side. If the second player played not on the left side but on the right side, we have just the exact same argument on the other side. The first player would respond with an S here and can force the win. So you see, games like this can lead to interesting. Here it's not too subtle, it's just a straightforward check the cases way of finding an optimal strategy, and the 7-box starting position is then easily seen to be a win for the first player. Now, the rest of the problem, which I didn't write down because I won't be analyzing it here for you, but it's a really fun thing to tease your brain with, and quite tricky, is what happens if you start with 2,000 boxes, 2,000 squares. Is that a win for player 1, or is that a win for player 2? So I'll leave it to you guys to try to answer that. The question also asks what happens with 14 boxes, which is surprisingly subtly different from the other ones. But the 2,000 box one was picked because, of course, this was the Olympiad in 1999, and 2000 was, of course, the next year.